Chapter 9, started out with geometric sequences for a reason. Do you remember back when we did arithmetic sequences back in chapter 3, what kind of a model an arithmetic sequence actually represents? If something is increasing by the same amount or decreasing by the same amount, it has a common difference, a common first difference, what kind of a function do we have? A linear function. It just keeps increasing. So if, let's pick a scenario here. How many of you get it, maybe you're past this age, I don't know. How many of you get an allowance? A weekly or a monthly allowance? Anybody anymore? Parents just hand out money now just that readily, you don't even have to earn an allowance anymore? Oh my goodness. Did you ever get an allowance? No? Huh. Gosh, things have really changed from when I was raising my kids. Okay. Well, what if, do you know what I mean by an allowance? What if your parents gave you a weekly allowance? And they said, they started this at the beginning of your 9th grade year, and they said, I'm going to give you an allowance of, they start you off with $1, and they say you're going to get $1 a week, but I'm going to increase your allowance by $1 every week throughout the rest of your high school, until you graduate from high school. So every week your allowance is going to go up $1. You're liking this, aren't you? Pretty good. Next week, so the second week your allowance is going to be $2. The next week it's going to be $3, and then $4. So you're thinking, wow, there's 52 weeks in a year. I have 4 years of high school left. I'm making a pretty good amount. By the time I get to my senior year, that last week of my senior year, my allowance is going to be fairly high, isn't it? Yeah. Okay. So then. That's when we have an arithmetic sequence. It increases by a steady amount. When we have a geometric sequence, what happens again? It's multiplied. So if your parents instead say it this way, I'm going to start you out with $1 allowance a week, and then it's going to double every week. So the next week it would be $2. Next week it would be $4. The next week it would be $8. Oh, which allowance do you want to get? Do you want to get the one where it increases by $1 a week, or do you want the one where it doubles every week? Yeah, the one that doubles. So it grows faster, and you should have noticed that about the geometric sequence, that if you have a geometric sequence, it is changing pretty rapidly. Those values are changing pretty rapidly. They can either increase or they can decrease. But you can have a pretty rapid change. So an exponential function is actually the function that a geometric sequence represents. Something that is growing at a multiplier rate rather than just a steady rate of so much being increased or decreased. So an exponential function is a function in which the independent variable x, we have an x and a y always in our functions, appears in an exponent. So your x in the equation is going to be up in an exponent. It has the form f of x equals a times b to the x power. So notice where x is. It's up in an exponent. And f of x can be replaced by what again? By y. Okay. So in this function, in this form, f of x equals a times b to the x power. A cannot equal 0. We're just going to b to the x power. B cannot equal 0. And we also want b to be a positive number, so we want b to be greater than 0. Now notice it doesn't say a has to be anything great. It doesn't have to be a positive number, negative number. It doesn't say there's any restrictions on a other than it can't be 0. But b can't be 0, and it has to be a positive number in the ones that we're going to study right now, okay? So it does not have a common difference. That's a linear function. A linear function is the one that has a common difference, but instead it has a common ratio. You know that thing we were looking for yesterday, if we were trying to determine if it was a geometric sequence or not? So if we find this set of numbers, a sequence of numbers, and it has a common ratio, it is actually, can be modeled by an exponential function, and that common ratio, that constant ratio is another name for it, is the value of B in the model. So we called it R yesterday. So in a way, what you can think of is you can think of it like this. We are talking about that R value we were looking for yesterday. It's now going to be the B value. It's the multiplier. Okay, really, really important. When you're going to evaluate an exponential function, you need to make sure you follow the order of operations. Because if you don't, it'll lead you to crazy answers that should not seem reasonable in many cases. Okay, let's go to page 628 in our books. Where we are going to look at problem number 2. The physics problem on that page. Everybody there? I've already written the function down for us, but what does this function represent? It says the function f of x equals 50,000 times 975 thousandths to the x power, where x represents the underwater depth in meters. Models the intensity of light below the water's surface in lumens per square meter. We're supposed to find the intensity of light 200 meters below the surface, and then we're going to round our answer. Okay, before we even do that, I want you to identify the parts of this. Does this look like an exponential function, first of all? What's our A value? 50,000. Okay. So what, that 50,000, anybody have any idea what you think that 50,000 is representing in this problem? What happened yesterday in that formula we used to find a certain term of the sequence? Like if it said to you, find the 10th term of the sequence, we had that formula we used, remember that? Okay. What do you think this 50,000 is really representing in a geometric sequence? The first term. Yeah. It's really the starting term. It's what are you starting with? So in this case, it's starting with 50,000. Well, what do you suppose the 975 thousandths, that 0.975, what's that?
That's the common ratio.
That's the common ratio. That's our multiplier. Okay, well, tell me something about our multiplier. Is it going to make this sequence grow? Would this geometric sequence keep getting bigger and bigger and bigger? Or would it get smaller as it went on? What do you think? Get smaller. Why? Multiplying by a decimal, we're multiplying by something less than 1. We're multiplying by a number between 0 and 1. A common number between 0 and 1 is 1/2. If you take half of something, does it get bigger? No, it gets smaller, doesn't it? So we're thinking that whatever our answer we get here probably should end up smaller than 50,000. We're looking, and we're actually looking for a missing term in this is really what's happening. It says, what is the intensity of light 200 meters below the surface? What's x representing in this problem? Look, what is x representing? The underwater depth in meters. And they said, this is 200 meters below the surface. So is this x? Is 200 x? What do you think? Or is it y? What is y representing, do you think? They didn't tell us that, did they? It says the function, where x represents blah, 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 models the intensity of light. So what's x and what's y in this? You told us what x is. It's the what?
Underwater depth.
Underwater depth. They said this function models what? The intensity of light in lumens. So that's our y value right there. So what is it that they're asking us to find? Are they asking us to find the depth? Are they asking underneath the water? Or are they asking us to find the intensity of the light? Which one are they asking for? the intensity. So we're solving for y in this one, aren't we? So what are we going to do?
Replace x with 200.
We're going to replace x with 200. Okay, and how about we put a y value here also? Let's just make it y, because that's what we're kind of used to. 50,000 times 0.975 raised to the 200th power. Wow, okay. So you wouldn't want to have to keep doing that 200 times, would you? Okay, what do we have to do first in this problem? Take 50,000 times 0.975, or 0.975 to the 200th power. Okay, and we're going to show what that actually is. We're crazy as that sounds. We're going to actually show, we're going to write that out on our papers. So, what is, go ahead and just do it from your calculator. You don't have to recite it out loud for me. What is 0.975 raised to the 200th power? And I'll write down what I got on my calculator, okay? Let's see. Is that what your calculator says? Something like that? Yeah? Okay, and so we have now taken that number to the 200th power. Is that
That's not a pretty.
it's not a pretty number. Is it very large? Very small. If you take a small number and keep multiplying it by itself, it keeps getting smaller, doesn't it? Yeah. And so now, I'm hoping your calculator just allows you to now just take that answer times 50,000. Okay, so then we can now, I think they told us what to round to. They told us to round to the nearest whole number. So we use the approximately equal to sign to show that we're rounding. And actually we rounded in the last step because I'm pretty sure that calculator wasn't even able to show us all of 0.975 to the 200th power. So rounded to the nearest whole number, what's the intensity, Jared?
316 lumens.
Yeah, this is 316, and what would it be?
Lumens.
Lumens, but I think we have to be even a little bit more specific than that. Lumens what?
Per square meter.
Per square meter. So I'm going to just abbreviate that as meter squared. It means the same thing. So for every square meter, there are 316 lumens of light, is what this, the intensity of the light is. Okay? It did get quite a bit smaller, didn't it? 50,000 to 316. Okay, and we shouldn't just do them though, without kind of like rationalizing through and saying, you know what really should happen here? Should I end up with a number that's larger? Because in the sequence, this is which term? In the sequence, this would be what? Which term? The 200th term. So it started at 50,000, and it kept going down, and by the time we get out to the 200th term, it's down to 316. And that makes sense. Okay. So you're going to be doing some problems like that, where you have to decide what do I need to put in where, and you show your work like this. Okay. Anybody have questions about that? Okay. Then let's look at, it says, to determine if a set of ordered pairs satisfies an exponential function, look for a constant ratio. In other words, probably don't want to have to graph it and see what the graph looks like, so maybe we could just do something like we did with our sequences yesterday. Okay, so in number 3, let's fill out our XY table for that one, because they gave it to us as a list of ordered pairs. Let's put them in table form. It oftentimes makes it easier to work with. So we have -1, -1, then we have 0, 0, then we have 1, this is a +1 now with a -1, and a 2, -4. Okay, first of all, the first thing you always want to check for is there a constant change in x? Is it going up or down by the same amount? Yeah, okay, the x's are going up by 1. Okay, so cool. Now we can check out what's going on over here. So we're going to do just like we did yesterday. We really could just treat this as We have -1 in our sequence, then it's followed by a 0, then it's followed by a -1, then it's followed by a -4. So we could start, remember how it's easier to start at the end so we make sure we divide properly? So the last term, the last y value divided by the previous y value, what is that? 4. And then we do the -1 now divided by the previous y value, which is 0. What's that? Can't do it, can you? Okay, zilch, that's undefined. And then we have 0 divided by -1, and that is 0. Would this be an exponential function? No, we don't have a constant ratio, a common ratio. We didn't find a common ratio. This is not a geometric sequence, right? It's kind of how you can think of it. So it would not represent an exponential function on the graph. In fact, anybody kind of looking at that right now and saying, you know what, I'm smart enough now, I think I know what kind of function that would be. Does it look familiar at all? Is it linear? Are the y's changing by a constant amount? Are they going up or down by the same amount? No. It's quadratic. Look at here. Where's the vertex at, in fact? At 0, 0. And look at how it's got that symmetric behavior starting. What do you suppose, if we had x equals -2 in this table, what do you suppose y would be? -4, yeah. So this one's actually, looks like it's quadratic. Okay, let's look at number 4. Would you fill out the table from your book? And again, we're checking to see if it is exponential by finding if it has a common ratio, that R value we were looking for yesterday, which today we're going to call B. Our x's are changing by the same amount, so then we can start doing our divisions. And look at what happens. We do end up with a common ratio of 4. Yesterday we would have said this is a geometric sequence with an R value of 4. Today, though, we would say this is what in our exponential function? The B value. Okay, so we're going to say it is exponential. With B equals, yesterday we said with R, today we're going to call it B, really the same thing. With B equals 4. That's an equal sign. With B equals 4. Okay. So to be able to tell without having to graph it, is it exponential or not? So you'll be doing some of that in your homework. But then I also want you to get familiar with the graphs of exponential functions. Okay, so let's go to that. And let's look at what do the graphs of exponential functions look like. Because we know what linear graphs look like. We know what quadratic ones look like now. Now let's see what do exponential ones look like. So I want us to, okay, now is when you can use your graphing calculator. So what do your graphing calculator? Go to y equals, clear out anything that is in there, get it out of there. And we're going to explore when a is greater than 0, in other words, our starting amount is a positive number, and when b is like it was in that number 2 that we just did from the book, when b is a number between 0 and 1, what does the graph look like? So it's kind of like saying, okay, how about what would the graph of that number 2 look like if we graphed it? What kind of behavior would it have anyway? So what you're going to do is you're going to type in 2. This is the one we're putting in right here. So we're going to put in 2, and then times, and then in parentheses, so start a parenthesis, and do 1 divided by 2. But before you close, oh, wait a minute. And then close that parenthesis. So it's 2 times 1 divided by 2, close that parenthesis, raised to, that upside down V, it's called the caret key, raised to, and then the x power, the x key. So we're putting it in like this, 2, and I think the times on your calculator might do something like that. And then it's 1 divided by 2, but it puts a fraction bar there for you. And then you're going to raise it to the x power. Okay? And then do a zoom 6 and see what it looks like. What's it doing?
It's kind of curving.
Kind of curving? Does it go into all 4 quadrants? No. Okay. So in other words, let's kind of just give a rough sketch of this. We're not gonna, we're not going to be exact. Does it look something like that? Kind of its behavior. So it isn't in all the quadrants. In fact, it may look like it, but it's never going to touch that x-axis. It's never going to get down there. In other words, this will never go into negative y values. It'll never even get to 0. It'll get so small, but it's never going to get to 0. So it begins in which quadrant? What quadrant? It begins in, remember we always do graphs from left to right. So it begins in quadrant 2. Okay, here, let's do this. I think some of us are maybe a bit confused about quadrants. So it begins in quadrant 2, and we don't use the Arabic way of writing our numerals like we're used to. We use the Roman numerals when we talk about quadrants. It begins in quadrant 2. And what's it doing from left to right? Rising or falling? It's falling. So it falls from left to right, approaching the x-axis in which quadrant? In quadrant 1. Or in other words, starting over here with x's, as we come this way, as x gets larger, as the exponent gets larger, remember to the 200th power, when a was between 0, or b was between 0 and 1, as x gets larger, what happens to y? It gets smaller. Y gets smaller. It's getting small. It's getting closer and closer to the x-axis where y is equal to 0. Okay, so that's when we have a positive starting value, and we have a multiplier between 0 and 1. That's what we should expect. Okay, now I want us to try it. Well, let's change it up a little bit here. We're going to start with a positive a value again, but this time we want our b value to be greater than 1. We don't want it to be between 0 and 1. I think I have to go to the front side too and change something that I did wrong there. And let's just go do it right now before I forget. Let's go to the front. I should have known when I was back there talking about it. This is b. It isn't that b can equal 0. We want b to not equal 1. That's what we don't want b to be. Because if it's 1 to the any power is still what? 1. There's nothing going on. So change that to b equals 1. I misinformed you there. Okay, now let's go to the back. When b is greater than 1 now it's the multiplier is bigger than 1. What should happen when you have a starting value that's positive and you're multiplying by something greater than 1? What should happen to the number, to the term that you're going to get? Should it grow or get smaller? It better get bigger, right? Okay. So that means the y value is getting bigger. As x gets bigger, so should y. Well, let's check that out on our calculators and see what it does. So I want you, again, now you're just going to put in 2, and you'll put in your times, and then you'll do 2 raised to the x power. You don't have a fraction this time, so you don't have to worry about those parentheses and that dividing. And so, and the calculator should take care of the order of operations on that. It should be able to do the power first and then go back and multiply by 2. Okay. So if your multiplier is bigger than 1, we're expecting that it should get bigger and bigger and bigger, our y value. So as x gets bigger, is y getting bigger? Yeah. In fact, is this the behavior right here? Is this what's going on? So just make a rough sketch of that showing that this is what, as you move across, as x gets larger, so does y get larger. So this graph begins in which quadrant? Quadrant 2. And is it falling or rising this time? This time it rises from left to right into quadrant 1. Okay. So notice there are no negative y values in either of these two that we tried. Okay, and those are the only kind that we're going to deal with right now. So we have a positive beginning amount, a positive a value, and then is our multiplier bigger than 1, or is our multiplier between 0 and 1? So summary for when a is a positive number, when it's greater than 0. The domain of y equals a times b to the x power is what? Remember, domain means which values? The x's of the y's. The x's. Okay, so what do you think the domain is? Look at your graph. Just look at that last graph you have on there. Are there any restrictions for x? Because look at over here. There's some x values being used right here. And those are negative x values. And this is just going to keep going, and it's just going to keep getting closer and closer and closer to the x-axis, but it's never going to get there. And over here now it's still going in the positive direction for x, and it's just going to keep growing and growing and growing, but it's going to, so the domain is all real numbers. There isn't an x value we can't use. Because we can even take things to the 0 power. Didn't we learn that this year? What happens when you take something to the 0 power?
It's always 1.
You get 1. Well then when you take, so if we took b to the 0 power, it doesn't even matter what b is right now. What would b to the 0 power be? 1. And what would 1 times the starting amount be? Same thing, the starting amount. So at the beginning, the starting amount would be our a value. Okay, and what's the range then? Positive, only positive. So how would we say that? As an inequality statement. Come on. Range is what? The y. So y is what?
Y is greater than 0.
Is greater than 0. Can it be 0? Does it ever touch the x-axis? No, it does not. So y is greater than 0. So we need to have a picture of what these graphs do also. Just like we have a picture of quadratics, that U-shape, that parabola. Just as we have a picture of linear, we need to know what do exponential functions actually look like. So any questions?